Molecular weight averages are useful because they give us a parameter that is representative of a typical chain length in a polymer sample, but they don't tell us anything about how widely distributed the chain lengths are within that sample. Another parameter that we can use to give us information about the breadth of the molecular weight distribution is called a Polydispersity Index. And this is calculated as a ratio of the weight average molecular weight to the number average molecular weight. So it's pretty simple. Polydispersity Index then is a number that is greater than or equal to 1, because remember we said that the weight average molecular weight is greater than the number average molecular weight. There's a special case if we have a totally fully monodispersed sample where all the chains have exactly the same length. In that case, the weight and number average molecular weights will be the same. You can prove that to yourself on your own using the equations, but for that case, the polydispersity index is equal to 1. But for any other non-monodispersed distribution, then this is going to be some number greater than 1. Typical values for a well-controlled polymerization can be in the range of 1.5 to 2. So this is a parameter that, again, gives you some idea about how broadly distributed the molecular weights are in your sample. So again, in a typical setting, you may be interested in calculating then these two molecular weight averages for a particular sample, and then you can calculate the polydispersity index and make sure that a product that you're producing or manufacturing has consistent properties in terms of the breadth of molecular weights associated with that sample. The other thing that I wanted to point out is that there are additional kinds of averages that can be used to characterize the molecular weight of a sample. We talked about number average and weight average molecular weight and how they can be used to define this quantity, the polydispersity index, that gives us a measure of the breadth of the distribution. Another kind of molecular weight is what's called the z-average molecular weight. And you can see how this follows the progression. So here, remember, the weight average molecular weight was the sum of the NI-MI squared over the sum of the NI-MI. And these product of N times M is related to the weight of the sample. The z-average molecular weight is the ratio of the sum of the product of NI-MI cubed divided by the product NI-MI squared, added up over all the components in our distribution. So this is another form of average molecular weight. A fourth molecular weight average that's sometimes used is the so-called viscosity average molecular weight. So this is defined as follows. It's the ratio of the product of Ni times Mi to the 1 plus A power divided by the sum of Ni-Mi. And all of that, this total ratio, is raised to the power 1 over A. And this parameter A has a value that ranges from 0.5 to 0.8, and that value is determined by the quality of a solvent. So a low value like 0.5 is representative of a poor solvent, meaning that the polymer doesn't want to dissolve well in the solvent. And 0.8 corresponds to a good solvent, meaning that the polymer wants to be or is thermodynamically favored to disperse within that solvent. We'll talk about what those mean later on in the course. In terms of the values of these parameters, as shown in this diagram below, remember we said that the weight average molecular weight was larger than the number average molecular weight. The z-average molecular weight you can infer would be even larger because now we're weighting the heavier fractions of the distribution curve even more heavily by raising them to the cube power here. So the z-average molecular weight is larger than the weight average. And the viscosity average molecular weight is somewhere in between the number and the weight average molecular weight, depending on the value of this exponent A. Okay, so why do we have these different molecular weight averages? Why can't we just agree on one and use that, or maybe just use the number and the weight average molecular weight, since those can give us a polydispersity index? Well, the reason is that different techniques that are used experimentally to measure molecular weight give us different components or different forms of the average molecular weight. So all of these are of interest because depending on what experimental method we're going to use to measure them, they're going to give us these different parameters, or in mathematical terms, different moments of this distribution function. So later on in the course, we're going to talk about some of these molecular weight characterization methods, and we'll see that some give us number average, some give us weight average, some give us viscosity average, and so forth. So for that reason, it's important to understand how these averages are computed, because depending on what kind of experiments we do to measure the molecular weight, they're going to give us different averages and different numbers. So it's important to understand what those are if we want to compare results that were obtained from measurements that were done in different ways.